Thanks a lot, Julia, and thanks a lot to all of you for waking up quite early. I guess many of you have had quite an early start today. Yes, so I'm Carola Schönlieb. I work here at the Applied Math Department, and I would like to tell you a little bit about mathematics involved in analyzing, manipulating images. So who of you has a digital camera? Who of you has a cell phone which has a digital camera? Okay. Who of you has done some image processing, some image manipulation using things like Photoshop or, I don't know, GIMP on the computer? Okay, that's good. So what I would like to do today is just to give you a bit of a glimpse into the mathematics actually involved in manipulating images, in extracting via these manipulations some additional information from these images. But before I do so, I thought that I'll quickly tell you a little bit about myself. Julia was very flattering, thank you very much. But I would like to tell you a little bit about how I got where I am now, because I think that, you know, for you at the start of your maybe mathematical career, this could be interesting. And then I'll start with some basics, give you some ideas about how you can think of an image as a function. I've said maybe the word image function before, but so the main thing that I'm dealing with are functions which are in the end images, and I'll do something with them. And then I'll just talk you through a few applications where you can see that these things are actually useful in the real world. And I'll start off with a kind of a fun example. Okay, so something about myself. You've heard that already. So I work here. I'm a reader here. I don't know if this tells you anything, but this is just one role that you can have at the university. So my research deals with mathematical methods related to image processing, image analysis, and I look at various applications related to those. So I work with biologists, with clinicians, with plant scientists, with a colleague of mine in the forest ecology group, and I work also with art conservators, for instance, and with artists. So I do this not alone, but I'm supported by a team of people. They consist of people from various stages. I have so-called postdoctoral assistants. These are people who have done their PhD and then go on in research. And then I have currently 4 PhD students, Veronica and Joanna, who work on biomedical imaging. Rob works on 3D conversion, which is the thing that you need if you have shot a movie in 2D and you would like to convert it into 3D. And Simone works on shadow removal. So if you have a photograph and you would like to remove shadows in this photograph. And then we also have usually some visitors. In this case, we have one from Paris, a French guy, and a lady from Denmark currently visiting. Okay, so just ignore most of the words that you see here, just to give you kind of an idea of what are the things that we are dealing with. In the mathematical topics, what you see a lot is the word analysis. So I really deal with functions and properties of functions and try to derive some information from these functions. And you see the word optimization. So I also usually try to frame my search for some information from an image as an optimization problem where you're trying to maximize or minimize a function. And you see computation here. Of course, if you deal with digital images, at some point the computer comes into the play and you have to think about how to actually compute these things. And the problems that we are looking at, you will see some of these later on. image restoration. So you have an image and there is something wrong with this image. There is noise, for instance, in it, or parts of this image are completely damaged, so you would like to restore them. Segmentation. So you have an image, for instance, and you would like to decompose this image into its constituent components, and many more. But we will see a few things later on, and I've talked already about some of the applications that we are interested in. So I thought that I'll tell you a little bit about how I got to where I am now. So this is more or less the timeline. Of course, it starts earlier. I also went to school as you did, which was also in Salzburg. So I'm Austrian originally. I grew up in Salzburg, where I went to school and then also started university there on the continent. It was for a very long time like this, that people were just staying at their local university. This is also now changing a bit, but that's more or less my path. Then so I finished my degree in Salzburg, my master degree in Salzburg, and then I went to Vienna for a PhD. Do you all know what a PhD is, a doctoral degree? Yeah. And then halfway through, I switched to Cambridge. I finished my PhD here. Then I went to Germany, to Göttingen, for a research position. And very soon afterwards, I became a lecturer here in Cambridge. And that's where I am since then. So, just a few more things about that. So the one thing that I would like to stress is, because this might also be the case for some of you, I don't know, but I'm the first one in my university with a degree at the university. So that was actually quite a challenge, because no one knew from our family how this would be. So kind of was just thrown into it. So I studied in Salzburg, quite a small department. When I started to study, the first thing I realized was that I'm not the best in mathematics anymore. So, you know, when you're in school, you're usually one of the best ones, or even the best one in your class. When you go to university, you realize there are more people like you around, and you might not be the best one anymore. But after you've overcome that, you just go on, and you actually find lots of exciting things and lots of interesting concepts that you are taught. And anyway, during my studies, I never thought about actually going for a career in research. But then the things changed by some things that just happened to you, which was that I got an award from my institute. And subsequently, one of our professors employed me in a research project. And that's basically how everything started. I really liked what I was doing. And I finished my master degree in this research project. And then I went on for a PhD. And I did not stick to my home university, but I changed. I changed supervisor, and I changed university. And I went to Vienna. And that was quite a big step again for me, because I grew up in this small city in Salzburg. I was always there my whole life up to then. And all of a sudden I had to change, and I went to the big city. Austria is not that big, but that's one of the biggest places in it. And I was all of a sudden part of a community of students, of international students. For the first time in my life, I was actually sharing my office with a female student, which was really a change for me, and that was really made a difference to my life and my work. And the good thing was that this department and the people there were very vital. So there were lots of things going on, and I was meeting lots of new people, I was collaborating a lot, so lots of research, lots of work in applied mathematics is actually is happening in teams. So you're not very often doing things alone, although you also need to do that. There is still the part of research where you go back to your office and you sit at your desk and you try to understand and solve a problem. But then you talk again with other people about it. And there were lots of things happening. I was traveling a lot. So this was also, you know, Vienna being the big city and me presenting this to you as the, you know, kind of the exciting new thing that I was facing in my life. Then there were many more things that happened. So I went to various places. Do you know where this is? Can you imagine where this is? There's a kind of a random beach, right? Sorry? South Pole? No. South Pole. Okay, so this is Los Angeles. They have not the South Pole. This is, well, you would not know where this is, but this is in Hungary, in Pest. There was a conference on arts and mathematics, and these are my two collaborators, the two artists in Vienna. This is Italy, and actually you can't see that here. So this is in the south of Italy at a place which is called Cetraro, and you see that we are working very hard there, but what you can't see is that just in front of us there is the sea and the beach, and you see that we also take some breaks sometimes and go into it. This is at the Willis Tower in Chicago. There was a conference there, and we went, and they had these glass cubicles where you could, actually quite scary. I did not do what this guy was doing. This was too scary for me, but you know, just pretending that I'm brave in this picture. So, and then, halfway through my PhD in Vienna, my supervisor decided to go to Cambridge. And so I went with him. And this was quite scary. It was the first time of me living somewhere else, so really living abroad in another country. Being at an elite university, you know, I come from Salzburg. This is a small city. So this was inspiring and scary. You're thinking of all these great people who came out of this institution. You think about men mostly, but actually there are also women here. So this is, for instance, Mary Cartwright, who did some very fundamental work in the analysis of dynamical systems, and she was the head of Girton College here in Cambridge for a while. And actually, when I came here as a PhD student, I was also a PhD student in Girton College, which was the first female college in Cambridge. Okay, so then I actually made it. I finished my PhD here. I graduated. Then I went to Germany for a while, and then came back to Cambridge. So this is more or less how everything worked. And to be honest, it's really, it's exciting, but it's hard work. And the exciting bit and the hard work bit luckily balance each other, so you carry on. Okay? And of course, you know, what helps, and I'm only telling you about my career at the university and these things, but what helps is, of course, that this is not the only thing that you have. You have family, and you have the boyfriend, and you have friends. Okay, this is in Beijing. We're eating hot pot here in a restaurant. This was actually quite an experience. And you don't only have human friends, but you also have others. In my case, I also have a dog, so who reminds me about the important things in life, like picking up food in the park and things like this. Yes, so this is more or less my life, and now let's go to the mathematics. So I just start with some basics, and those basics will become a bit clearer once I go to the fun examples in the end to see why we are doing all of this. Okay, so we talked about your digital camera, your cell phone. What is it actually that you acquire with your digital camera? Well, if you look at a digital photo like this, you just see a photo of the Tower Bridge. If you zoom in, and here I'm zooming in into this Union Jack flag here, you see that actually this image, and then you can zoom in even more, this image is made up of these squared areas here, which are called pixels. And what you see as a tower bridge here is nothing else than a collection of these squared areas, these pixels, where in each pixel you are storing an intensity value, a gray value. Okay? And this gray value ranges from 0 usually to 255, where 0 is black and 255 is white. Okay? So you can also think about this as a collection, a huge collection of numbers, and this is what you then see visually as the tower bridge. Okay? So this is really a function. Let me tell you that this is a function. This is a function. So I told you that I'm worried about functions. And the functions I'm worried about are these images. So you can think about this as a function, and I call this u here, which maps to every pixel, and the pixel is here encoded in a pair of two numbers, which are the coordinates of my pixel in this image. Okay, so these are those guys here. So pairs of two coordinates give me the position of one of the pixels, and I assign to every pixel here, and this function, this image function u, is assigning an intensity value, a gray value between 0 and 255. Okay? You stop me if there is something not clear. Good. So this is grayscale. Usually in the modern world, we actually have color images. How does color come along? Color is the same process as here. The only difference is that instead of having in each pixel, you're storing one intensity value, you're storing 3 intensity values, 3 gray values, one for red, one for green, and one for blue. Okay? So you have basically 3 such collections of numbers that you're dealing with. Okay? Okay, and this is just to show you that this is really a function. Okay? If I think about the grayscale intensity in each pixel as the height of my function in z direction, let's say, and you plot that, this is x, this is y, let's say, and you're plotting u of this position, which is one of these values, then you will get a function like this, and this for this case here, it looks like this. Okay, so you can see here, yeah. So you can see here part of the eye of this lady. Okay. Okay, so this is a function. So if it's a function, we can do some mathematics with it. Okay. So what can you think about doing with this? Well, one of the things that is one of the key things that people in image processing and analysis are doing is smoothing an image. When you have, for instance, some corruptions like noise or something like this, you would like to clean them, you would like to smooth them out. One smoothing process is averaging. Okay? Think about the following. This is your image. Here you have some pixels. And what you do now is you look at this gray value that you have here in the center pixel, and you replace it by summing up all its direct neighbors together with itself and divide it by the number of pixels you have summed up. And then you replace the center pixel by this average, right? This is an average. Okay, is that clear? And you do this for every pixel in your image. You look at its neighbors, and you sum up the neighbors and you replace the center pixel by the average over all its neighbors. You can do this average also in a bit of a more clever way by saying you do not weight in this average all the pixels in the same way, but you say actually the center pixel is still the most important one. Okay, so this has the highest weight. And the other ones in the neighborhood, they are weighted a bit differently. So they're weighted a bit lower than the center one. And then you are summing up, you can't see all this, but then you're summing up over all your pixels with a different weight. Okay? You can see it actually here. So you weight the center pixel higher and the other ones a bit lower. Okay, and this is called Gaussian filtering, Gaussian smoothing. So let's see what this is doing to your image. Let's go back to an eye, an image of an eye. This is your original one. If I do this process with summing up over a window that has the size 5 cross 5 cross 5 pixels, then you get an effect like this. Forget about this for a moment. This tells you how much your weighting function, how much you are actually emphasizing the center pixel. So then what you see is that what you get as a result is an image, again of an eye, but with some of these fine details here removed, right? You have averaged them out, right? These fine details in the skin, for instance. You can do that again. You can also do that with a window that has a larger size. So you're averaging more, and then you get something like this. Okay. What happens if you do that again and again? What happens if you average more and more and more and more with this image? What do you think happens? Yeah?
Maybe completely blurred.
Sorry?
Maybe completely blurred at some point.
Yes. And what happens if I do this infinitely, well, I don't even have to do it in this case infinitely often, but let's say I do this forever.
Great.
Just one, it will be just one constant thing, right? It will be just one constant thing. Okay, so good. Okay, thank you. So that's what's happening. Okay, so this is one thing, and this comes back to us later. That's why I'm telling you this. So this is one thing you can do. You can manipulate an image by averaging, for instance. Okay. What else can you do? Well, this image I've told you is actually a function, and I've shown you this 3D surface that you can think of as the function. You can also think of it when you just cut through if you just look at one section through this image and plot all the intensities along this line, then you get a 1D function which looks like this. Okay? So one of the things that people are very often interested in when they analyze images is to detect edges in images, to detect boundaries between different objects. And this, for instance, is useful if you would like to isolate objects in an image, because you can say the boundary between an object and its background is given by an edge. For instance, here the eye would be outlined by something like that. Okay? And you can see that also in the function, in the image function. These will be the areas where the function is changing a lot, right? Where something jumps from a light gray value to a dark one. So this could be an edge. How can we quantify, how can we somehow use this idea that edges are where the function changes a lot in detecting them? Well, think about derivatives. Okay, think about derivatives. What is a derivative doing? It tells you how much a function is changing, right? So if you look at this function here, then you could think that this function has two edges, one here, where something is changing from a low gray value to a large gray value, and then here back again. And this could be an object, okay, that you want to detect in your image. So you would like to see where these edges are. Well, if you look at the derivative, this looks like this, right? You can also differentiate twice, then it looks like this. And how does this look when you do this actually to the image? So you haven't yet learned about differentiating functions which are defined by which are defined in two variables, right, in x and y. But just think about the derivative in this case as taking a derivative in x direction and one derivative in y direction. And summing them up, you get something like this. So this is the first derivative. So you can see that you have where the edges are, you have high values of the first derivative, right? Maxima and minima of the derivative. What I'm showing you here is the same thing, but the derivative of the smoothed of this filtered version of the image. What you see in particular, where you can see that smoothing is sometimes helpful because you can see the edges in this case much clearer because they're more robust. They're already kind of averaged to give the main position of these edges. And you can differentiate twice. Okay, so this is what this gives you. We have seen when you differentiate twice, the places in your function where the function changes a lot are given by the places where the second derivative crosses 0, right? And again, you can see that this is accentuated here around the eyelid and the eye. Okay. Okay, so these are the things that you can do, but why do you want to do them? So let me give you a few examples. Okay. And the first example is mitosis analysis. Can anyone tell me what mitosis is? Does anyone know what mitosis is?
The division of a cell into two.
Yes, perfect. Thank you. Thank you. So what we want to analyze in this case is how cells divide. And in particular, what we want to understand is how cells divide if they're treated with a cancer drug. So imagine a patient has cancer. Many of the cancer drugs that are around, like chemotherapy, what they really would like to do is they would like to prevent the cancer cells from dividing. Okay? So in order to develop these drugs and in order to analyze them, what you do is you look at cell cultures. You will see this bigger on the next slide. You look at cultures of cells. Okay? You treat them with a drug and you see how they behave over a particular period of time. And you look at how they behave by actually imaging them with a microscope. Okay, and this microscope then gives you a sequence of such images where each of these images corresponds to one particular one particular state those cells are in at one particular time. Okay, so this is like a video. Okay. Okay, and what we would like to do is we would like to understand how those cells divide, and in particular what we are interested in to develop mathematical techniques to help us in this analysis of the mitotic cells. And the two main things we are interested in is how long does it take the cells to divide. So this is also effectively proven that this will be affected by the kind of drugs that you're giving to the patient. And how does it determine the fate of the cells? Do the cells really divide, or do they die? We hope they die. Sometimes they might not just divide in 2, but maybe even in 3 or 4. Okay, so this is what these drugs can do to your body, and this is just a close-up of the things that we are looking at. This is a cell, this is another cell, this is another cell, and so on. and they are swimming around, and while they are swimming around, they are dividing or dying or doing nothing. Okay? And what we want to do is we want to detect those guys which are dividing or dying and ignore all the rest of this image. Okay? So, what we are interested in is this kind of analysis where you say you have this culture of cells, this collection of cells, you monitor them over time, and you would like to understand how many of them, when they go through mitosis, only interested in the one that are mitotic, that are actually dividing. Do they survive? If they survive, do they divide in 2 daughter cells or maybe more daughter cells? And if they don't divide, do they die? Or sometimes they just seem to be doing something and then they just go back to their normal state and they don't divide. It's not successful. So, why is this interesting? I just said it before. Because people would like, in cancer research, would like to develop drugs which are killing the cancer cells and which are preventing them from dividing. So how do you do this? Okay, I'm not a biologist. You need a biologist for that, of course. And in this case, the images and the problem was actually asked, the question was asked, and the images were acquired by a colleague of mine from the Cancer Research Institute here in Cambridge. This is Stefanie Reichel, and I'm just saying here the art biologist because she is not only a biologist, but she's also an artist. Actually, my life is kind of accompanied by these artists that I meet. So also to show you that actually science and arts do not have to be distinct things. There are people who are doing both. So you need a biologist. And you need a mathematician. You need a flying mathematician in this case. So this is Joanna. Joanna is a PhD student that is jointly supervised by Stephanie, by the biologist, and myself. And apart from the fact that she can fly, she is also really a great mathematician. Okay? This picture will come back to us. I will explain to you how she is flying. So what we want to do, or what we have done, what Joanna has done really, is outlined here in these 3 steps. So if you look at this sequence of microscopy images where you have these cells and so on, you first would like to isolate to detect those ones which are actually going through the mitosis. Okay? And this is what is done here. Okay, so you detect the ones which are mitotic, and I explain this to you in a second how this is done. And then, once you have detected them, you would like to track them, you would like to follow them all the way through their cell division. Okay, all the way through their mitosis, and you would like to determine what is happening to them in the end. Okay, in this case, they're dividing in 2. And then you would like to take all of this and you would like to make it as automated as possible such that so why are we doing all this? Because we would like to help the poor biology PhD students who are otherwise sitting in front of these images and doing all of this by hand, right? So in the end, what you would like to do is to create a kind of a software tool where you can just load in these images and then press a button and everything works. In the ideal scenario, okay? So the first step, how do you detect these mitotic cells? And the one thing, this is again why you need to collaborate on these things with biologists. The first thing you need to understand is what is the difference between a cell, floating around as usually, between a mitotic and a mitotic cell. And the first thing that they tell you, and that you actually also see, is that at some point, more or less in the middle, so this is the whole mitotic phase, somewhere in the middle, these cells round up. They round up, and in the microscopy image that you see, they develop this halo around them. Okay? So this is one example, this is another one. So how can we use this? Well, we use this by a mathematical technique that detects circular objects in images. Okay? Well, we know that they are circular, so let's detect all the circular objects in each of these images in the video. And for doing this, there is a guy that is called Huff, who developed a transform initially to detect lines in images. Okay? So how does this work? Let me actually draw a picture quickly. I don't know, can we switch on maybe the light? Perfect. So imagine that you have an image like this. Okay? And imagine I will only explain to you how the line detector works, okay? And the circular, you can imagine that this can be generalized. So imagine you have an image like this, and this image has nothing else in it for simplicity than one line like this, okay? A very boring image, but that's how it is. Okay, so what this Huff transform is doing, it's taking, we have seen that the image is a function, and a transform is something that transforms a function into something else. Okay? And how this works is that you basically you look at lines. So you look at lines through your image with different, let's say this is my origin, okay? With different intercepts and with different slopes. Okay, so you can also change the slope. Okay, this gets messy now, but more or less you do this. You do this for a particular range of slopes and a particular range of intercepts. And while you walk along each of those lines taken through the image, you record all the intensities that you visit in each of the pixels. So every time you're hitting a pixel, you record what the grayscale in this pixel is. And in the end, for each of those lines, you are summing up all the grayscales along this line, and you record them in this new function, which is the Huff transform. So now the Huff transform is now not a function of x and y, right? In this case, we had x and y. This is my image. But this Huff transform is now a function of the slope and the intercept, right? For every slope and every intercept, you're recording one value, which is the sum of these pixels along the line. So this is a function of the slope, and the intercept is called b. Okay? So now if you look at this, what do you think this will give you? How do you think this can help you to detect this line? If you sum up now over a line, over this line, for instance, okay, over this one, which has slope 0 and some intercept b here, then in this image, where you sum up over all those guys, this will give you the maximum value, right? Because here, this is the only place where you have white. Let's say this is all 255 along here, and all the rest in the background is 0. So this will give you the maximum, okay? And you can see this. Sorry, I'll switch off the light first. You can see this. Too big of a stage for me. You can see this here. Don't mind, this is now parameterized differently. You know that you can parameterize lines differently. This is now parameterized in terms of the angle that the line makes with the x-axis and its distance from the origin, its normal distance. But anyway, what you see is that in this case, those two lines are indicated by those two maximum values in this new image, which is the Huff transform. And so this gives you a mean to detect those lines in the image, right? But we don't want to detect lines, we want to detect circles. So with circles, you do something similar but instead of summing up along lines, you're summing up along circles. And then the same thing happens if you're hitting, you know, the boundary of your circle, you will get the maximum value, and that's how you detect those guys. And you can do it then. So, and this actually works quite nicely. You detect the circular guys in your microscopy images, the ones which are mitotic. And once you have done this, then you start from, let's say here, from the circular shape, you're starting to track those cells forward in time till the end of the mitosis and backward in time till the start when they actually started to think about being mitotic. Okay? So this step was easy. This step is not that easy. And so just to give you a motivation to carry on studying, this is what you need to do, okay? And I don't expect you to understand this, of course, but because it takes some years to understand this. But what you see, again, is what is important here are some concepts that you're actually learning now, like integrals. The integral here before was actually, I replaced it by a sum, okay? Derivatives of functions. Derivatives in 2 dimensions are indicated here by what is called the gradient. So you need derivatives, you need integrals, you need all these things, okay, in order to do this. And then in the end, you will be rewarded by something that actually works. So you have the software tool. You first, this tool will detect the mitotic cells in your image sequence, and then it tracks them one by one. It tracks them through their mitotic phase, and then in the end, it spits out some numbers about how long did the mitosis take and things like this. Okay. Good. So let's speed on. What else? Arts restoration. Arts restoration is another thing that I'm concerned with, and to actually restaurate paintings and frescoes and manuscripts. It's the same technique that makes Joanna fly. And of course, now you see I'm revealing the mystery. She's not really flying. What we did in this case is using an equation, okay, that interpolates, basically takes the stool she's sitting on and interpolates the color values in the neighborhood of this stool and replaces the stool by this interpolation. Okay, and this is called in-painting. Okay, so image interpolation, and then you can do things like this. You see that, depending on how you're dealing with that, you get better or worse results. So it works quite well in these areas where there's nothing much happening. It doesn't work that well here, because so there you can see that actually all of this is highly non-trivial, because what you need to do for this interpolation is really to capture not only the colors, but also the structure that you want to propagate into this domain of the stool. Okay? But so these are the things that you can do. Sometimes, another example is when you have a photo and someone scribbled over it, and you would like to restore what was actually originally in this picture. And you can do things like this. This is the same equation that we used in order to do this. When I say we used an equation, what I mean by that is that you need a law that tells you how to interpolate these color values inside the gap, okay? Where the gap in this case was given by the heart. And then you can do that for actual really useful things like forensics, where imagine you have a crime scene and you find a fingerprint, and then you want to use this fingerprint and match it with your database and find the guy who committed the crime. Very often these fingerprints are not as nice, okay? Not as nice in the sense that it will be quite hard for an automated search tool to find the corresponding fingerprint in the database, because the fingerprint has these gaps and things like this in the lines that actually make up the fingerprint. So what you do is, in order to enhance and help this matching method, is to make the fingerprint better, and in this case interpolate the lines that are missing. And now let's go to art. So this was one of the first things that I did in my PhD project in collaboration with some art conservators in Vienna. These are frescoes, the so-called Mitotic frescoes, medieval frescoes, which were forgotten for a very long time in an apartment in the center of Vienna. And they depict scenes of the songs of the Minnesinger Neidhard von Reuenthal. Okay? So those are profane frescoes, and some rich merchant in these days commissioned an artist to actually paint them. And then time passed, and at some point the church got hold of the building. And those are profane frescoes, you know, showing these knights and maidens together and so on, like here. So the church really didn't like that, and just overpainted the fresco. So what they did a couple of years ago, like 20, 30 years ago, they found this fresco again, and they removed the paint, but with the paint they also removed some parts of the original fresco. Okay? And so what we did there was to help the actual restorators by creating a visual template of how the restoration could look, again with an interpolation method that falls back to an equation like this, which again involves the image and some derivatives of this image and so on. And then we came here to Cambridge, and then we found someone here from the Hamilton Kerr Institute, which is a conservator institute, and they give you paintings like this. So this is almost impossible, right? So this was actually almost impossible. Not just for us, but also for the physical restorator. So in this case, it's even more important to have something like a visual template, because it could tell them how it looks if they do something or something else with the painting. So if you look into here, so just this shepherd here, what the French visiting student was doing is, so this is the detail, and then this is when you just remove some of the small corruptions that you have, and this is when you do the whole thing. Okay. You can do also funny things like this. So digital restoration is quite important for people who are looking at illuminated manuscripts, because the usual thing is that they do not touch them physically. So they're really interested in creating a digital template. So this is a manuscript from the Renaissance, and what you see now is not the original manuscript, but it's the manuscript sometime after the Renaissance. People became pruder and overpainted Adam and Eve with skirts, so they didn't want them to be naked. So what we did then is, so you have these skirts. They weren't originally there. So how did the painting originally look? Well, there are these cool imaging techniques. So in this case, this is infrared imaging, which looks not only at the visible light spectrum, but which can actually give you information about the invisible light spectrum. And then you can look underneath, and you see what is underneath. And you can use that structure that you see underneath to actually get back Adam as he was, and then you can actually get some sense of how this scenery might have looked like originally. And I would like to just finish by some fun examples. Okay, so this might not have such a real-world application, but this is just fun. So you have two images, and you would like to somehow merge them. Okay, so you would like to get some features of one and some features of the other and make something in between. So So in this case, we have Obama and Reagan. The first thing you would like to do if you want to somehow merge features in two faces with each other, you want to detect these features. So here the eyes and the nose and the mouth. So they are detected here. I don't know if you can see that. There are some green dots here, which are the points of the nose and mouth and so on. And then what you do, the first thing you do is, if you want to match, let's say, the nose and the eyes and the mouth of Reagan with the ones of Obama, you first kind of stretch Reagan's face such that it fits into Obama's. Okay? And then there are some other steps involved, and then you can create something like this, which is basically taking the wrinkles of Reagan, putting them onto Obama, also taking the nose of Reagan, and yeah, I think that's more or less it. And the eyebrows, of course, they're also Reagan's. Okay, and just to explain that, yeah, so this was just what we see. You can also do it the other way around. You can make Reagan younger by taking the skin from Obama and putting it here. And you can also replace the nose of Reagan by the one of Obama. And the process, just to give you a conceptual idea how this works, how do you decompose your image into things like wrinkles and larger scale features like the nose and stuff like this? Well, think about this Gaussian filtering that we did at the very beginning. You started with an image with all kinds of fine scale and large scale features. And then as you go along this smoothing process, you are losing more and more of these fine scale features. So if you think about subtracting now this image from this one, you might get back the wrinkles, things like this, okay? So then you can somehow decompose them. So do you guess who is this? Well, this is Mona Lisa, and this is, sorry? No, actually it's again Reagan. It's again Reagan mapped onto the Mona Lisa. Here is Reagan and the Jesus statue in Rio de Janeiro, the Christ statue, slightly aged. You can put Reagan onto the Statue of Liberty. You can put him onto, what's it called, Mount Rushmore, right? This is Washington, I think. Yeah, you can do all these kinds of things. So you can play around with it. Because we are mathematicians, I'll just show you here Gauss Newton. Okay, Gauss, well, also reflecting that I spent some time in Göttingen, and then I'm spending some time here now. This is Newton. You can merge Gauss and Newton, put some features from Newton onto Gauss. This almost looks like a clown, right? I mean, almost like a... and then you can use Newton and match some features of Newton onto Gauss. Some features of Gauss onto Newton and things like this. Okay, so I'll finish here, and I'll just want to say that I hope I gave you some ideas of what kind of things we mathematicians who are working with images are interested in. The mathematical things that you need are functions and derivatives of functions, and some more advanced things that you can do with those concepts. And you need ambition, and you need love for the subject. And if you want to, do things with applications, you learn a lot also about the other disciplines. So you also need to be interested in mitotic cells, for instance. Okay, so I'll finish there, and I thank you a lot for your.